Hello and welcome to the beginning of rotations. Before we start rotations, we're going to briefly talk about the fact that we have learned 3 of the 4 transformations so far. In this first example, it talks about what type of rigid motion that A would be ABC, triangle ABC would become triangle A prime, B prime, C prime. When I'm looking at this example right here, it appears as though the triangle was reflected over the x-axis. So type of rigid motion is a reflection. Is size preserved? Absolutely. Is orientation preserved? No, because we have an opposite isometry. And what kind of isometry is it? An opposite isometry. So in this first one, it's a reflection. Orientation is not preserved, and it's an opposite isometry. Moving on to the third example, which is this one over here, it seems as though it was a translation because the triangle was simply shifted down a couple of units. So in this case, A became A prime just by moving down. So what I'm going to do is I'm going to fill in the word translation for type of rigid motion. Is size preserved? Yes, absolutely. Is orientation preserved? This one it is, and it is what we call a direct isometry because orientation is in fact preserved. In this last one, it might be kind of hard to see, but we are actually rotating this triangle around the origin. If we were to rotate our paper, which is what we're going to talk about today, then it winds up to be triangle A prime, B prime, C prime. So this one is in fact what we call a rotation. Is size preserved? Absolutely. And if we look carefully, the ordering of the letters plays a very important role. And you will see that the ordering of the letters is in fact counterclockwise, and on the A prime, B prime, C prime, it is also the same counterclockwise. So in fact, in a rotation, orientation is preserved, and because it is preserved, it's considered a direct isometry. So please make sure that chart is filled in. Then we're going to take a look at the bottom half. So on the bottom here, it talks about a rotation, and rotations are super important. They are a big part of geometry. So a rotation is a rigid motion that turns a figure about a fixed point called the center of rotation. A lot of times the center of rotation is in fact at the origin, but sometimes it's not, so we'll talk about that later. The angle of rotation is the number of degrees that a figure rotates. So a positive angle turns the figure counterclockwise. That would be like positive 90 degrees or positive 180 degrees. And then it says a negative angle of rotation would turn it in the opposite direction. So that would in fact go clockwise. And what that would look like is this rotation, and that would be negative 90 or negative 180 or negative 270. So let's take a look at some specific examples. On this next page, we have 4 different examples of the coordinate 4, 2, and they're going to be rotated. So the first thing I'm going to do is I'm going to zoom in on 90 degrees. And what you have to do is you have to rotate your paper as though it was rotating 90 degrees. If you look carefully, it seems as though my paper is sideways, but I also did a rotation. If I was to figure out the coordinates of this point right now, they are in fact negative 2, 4. So I'm going to turn my paper back. The coordinates of the new point would in fact be negative 2, 4. And if you plotted it, it would be right here. So there's a general rule that we're going to follow, and that is in fact, if we started at 4, 2, if I started at xy, the new coordinate winds up to be negative y, x. Let's take a look at the next one. In this case, we're talking about rotation of 180 degrees. So I'm actually going to take my paper and I'm going to rotate it. That would be 90 degrees. And then if I rotated it another 90 degrees, I know it appears as though the whole thing is upside down, but the coordinates are in fact negative 4, negative 2. Now, when I turn my paper back to where they were supposed to be, and if I plotted negative 4, negative 2, I would have the coordinate there. -4, -2. You will realize that in this case there's a rule. If the coordinate starts as x, y, the new coordinate is going to in fact be -x, -y. And it's important that you can see that it would be -x, -y. We've actually learned this rule before, and this one is exactly the same as a reflection in the origin. So write that down somewhere, please. 180 degrees is the same as a reflection in the origin. Moving on to in this next example, we were talking about rotating the paper 270 degrees. So this would be 90 degrees, this would be 180 degrees, and this next one would in fact be 270 degrees. So the coordinates of this point would in fact be 2, -4. When I turn my paper back to the original, I would then go ahead and plot 2, -4, and you'll notice that we're making our way around the different quadrants. So the coordinate would be 2, -4, and we could look at the rule for this one. X, y would in fact become y, -x. So it would become y, -x. Okay, we're going to take a look at a rotation of 360 degrees. This one seems a little crazy, but I'm going to take the paper, rotate it 360 degrees. Notice I just flipped the entire thing all the way around, and the new coordinate is still, in fact, 4, 2. So the rule for this one, it almost is like it doesn't exist. X, y stays as x, y. All right, so let's take a look at the rules at the bottom of the page. On the bottom of the page, we have a couple of different rules. It says a rotation of 90 degrees. So the rule there would have been -x, y. The rule for a rotation of 180 degrees would have been -x, y. And the rule for 270 degrees would have been y, -x. Now, we will certainly look at more of these in class, but that's the basics of the rules. If you wanted to, you could add a rotation around the origin of the coordinate x, y would result in x, y. So remember, rotation 360, nothing really changes. Thanks, and I'll see you tomorrow.